Hello friends, my name is Abdul Sami Mandal and today I'm going to present you my seminar topic which is flow-based reinforcement learning. This topic comes under machine learning and my guide is Dr. Sunil Kumar Khen, who is the professor and HOD of Department of Information Science. So the contents of this seminar is first I'll be giving you a brief introduction and then we'll be looking into related background of this topic, which is flow-based reinforcement algor flow-based reinforcement learning. And then I'll be discussing the literature review with you guys. And then we'll be looking into the working and the implementation of flow-based reinforcement learning. And then we'll be looking into the future enhancement of this topic. Then we'll be discussing the conclusion of what we learned in this topic. And finally, I'll be discussing the references which you guys can refer to learn more about this topic. So first, let's look into the introduction. So flow-based reinforcement learning is a method used in artificial intelligence and machine learning to teach agents to make decisions in dynamic environments. In this approach, agents are trained to understand and optimize the flow of resources. So, flow of resources, information, or other entities within a given environment. Flow-based reinforcement learning algorithms typically involve modeling the environment as a graph or network, where nodes represent entities such as vehicles, products, or data, packets, and edges represent the connections or transitions between them. And flow-based reinforcement learning algorithms typically involve, sorry, so flow-based reinforcement learning algorithms typically involve modeling the environments, such as a graph or network, where nodes represent entities, such as vehicles, products, or data packets, and edges represent the connections or transitions between them. Agents learn to make decisions that maximize the efficiency, throughput, or other relevant metrics of this flow, often using techniques such as deep reinforcement learning. The simulations are conducted in two environments focused on maze navigation and reward collection. Next, we will look into the related background, or which is the prerequisite knowledge required for this. So, planning and hierarchical reinforcement learning. Now, one of the fundamental challenges addressed in modern reinforcement learning literature is the long horizon problem. The long horizon problem refers to tasks that require a substantial number of interactions with the environment to be completed. One such technique is hierarchical reinforcement learning, which involves learning low level policies that operate only in short horizons and high level policies that leverage low level policies to solve long horizon tasks. Next is goal condition reinforcement learning. So, in this approach, the first step involves identifying waypoints, referred to as landmarks. These landmarks are then represented as vertices, and a graph is constructed by using a value function to define the estimated distances between each pair of landmarks as edges. Subsequently, planning is performed using the constructed graph to guide the agent towards the goal. The third one is zero shot transfer for goal conditioned reinforcement learning. To enable the deployment of a reinforcement learning agent in real world applications, it is crucial for the agent to be able to learn and perform new tasks without interaction and offline data. Fourth one is diffusion model. The diffusion model is designed to sample data points from a target distribution and modify the sampling target using SDE. Next, we are going to discuss the literature review. So, the two main papers that I have referred for this seminar is the first one is The author and publisher, they are XHE and CLV. This was published in IEEE Trans Artificial Intelligence, Volume 5, Number 1, paper 244 to 253, and it was published on Jan 2024. The title of this paper was Robotic Control in Adversarial Sparse Reward Environments, a robust goal condition reinforcement learning approach. And the analysis from this paper, which I have gathered, is with deep neural networks based function approximators, reinforcement learning holds the promise of learning complex end to end robotic controllers that can map high dimensional sensory information directly to control policies. And the base paper, the second paper, is also the base paper which I have chosen for this seminar, and it is published by Wongyam Song and Jungwoo Lee. They are the senior member of IEEE, and it was published in 20th February 2024. The title for this was Ricky Planner, Zero Shot Transfer for Goal Condition Reinforcement Learning via Geometric Flow. And the analysis which I have gathered from this paper is initially we identify the shortest path on the simpler manifold and subsequently convert it to the shortest path on the desired manifold by applying the inverse process of the Ricci flow. So in this paper, they are mainly discussing about the Ricci flow, and they also have devised an algorithm known as the Ricci flow algorithm. We'll be discussing about it later. Now we'll be discussing the working and implementation of this project. So as we can see here, the visualization of the path generation process in Wiki Planner on a randomly generated maze. So this maze is randomly generated. So the left four figures illustrate the progressive transformation from a simple manifold to the target manifold. As you can see, the left four figures, the leftmost figure is a straight line, and then slowly it starts bending and merging and creating a wave. So it is generating a maze randomly by itself. So what happens is the left four figures illustrate the progressive transformation. As we can see from as we move from left to right in the figure, we can see that a progressive transformation is happening from a simple manifold to the target manifold, depicting the shortest distance on each manifold. And the rightmost figure, as you can see here, is the actual maze environment and the final resulting path. Now we'll discuss about the proposed flow-based reinforcement learning model. So the first thing is environment, the environment in which the model is. So from the environment, the mod agent will have a local visual observation, which I've denoted using the variable st. Then the environment is also going to have compute reward. So what happens in reinforcement learning is that whenever the agent executes a task, a reward is given to the agent. So the reward I have put as RT. And then in the reward, there are two types of reward. First one is confidence reward, and the other one is observation reward. So after computing both of these, the reward will be given. The reward is then given to the agent. As you can see here, if you follow the arrows, and then the agent will, after receiving the award, it will be executing an action in the 2D space, and then the action will be implemented in the environment, and this cycle repeats itself. So this is the major algorithm in this paper, which is the Ricci Planner algorithm. So the input is current state, which is S, goal state, which is G, and sample points, which is D. And the output is sequence of sub goal, which is PI, which belongs to the subset N. So first of all, we'll be initializing. So for I is equal to 0 to N, we'll be doing P of I is 1 minus I into N S plus I into N G. And then we will update for t is equal to capital T till 0. We'll do P of T implies P of T of D, which is a density estimation. Then we will set pi t, sorry, lambda t by substituting P of T into 7, which is the seventh equation. And then we'll start another loop, which is for j is equal to 1 to s. We'll calculate, we'll calculate sigma L sigma x I of n belongs to n using 6 and 16. Then pi of I into I belongs to n, and pi of I into I belongs to n, which will come under make regular algorithm, which is another algorithm we'll be discussing later. And the result which will be returned is pi of I into I belongs to n. And this is the algorithm 2, which is make regular. The input for this is point sequence pi of I into I belongs to n. This is the output which we get in Ritchie-Planner algorithm. So then output will be regularized point sequence. So first we'll be starting a loop which is for k is equal to 1 to k. We'll do I naught is 0, L naught is 0 for I equal to 1 to n. Then we'll start another loop. L of I is P of k into I minus P of k into I minus 1. And L of I is L of I minus 1 plus L of I, which is the capital L of I and small l of I, both are different. Then we'll start another loop which is for I is equal to n1 to n minus 1. We'll do L is P of nj is equal to 1I, and tau is L of n into I of n. Then P of k plus 1 into I k is tau into P of k, and P of k plus 1 naught is P of k naught, comma P of k plus 1 n implies P of k n. And then we will return P of k of I into I, it belongs to n. And then we have algorithm 3, which is randomized trim. So the input for this is weight W and height H. The output will be cell state matrix S. S is cell state matrix of size W into H. S of odd is wall and S of even is room. And C is 0, 0 and Q is subset of C. So while Q is greater than equal to 1, we'll do C is Q dot pop. Then C dot visited is true. And N is cells with a positional difference of 2 partition N into visited V and unvisited U cells. So if mod of V is greater than equal to 1, then D is sample one cell from V. Denote the cell between C and D as room. Then Q dot extend and the parameter is U. And then we will return S. So simulation environments. As you can see in the left, we have illustration of the shortest path and initial path in a randomly generated maze. So on a Riemann manifold, given arbitrary path xt and the length Lfx is defined as a continuous functional on the path space. Therefore, in optimization perspective, finding the geodesic between 2 points is equivalent to finding the minimizer of the functional on the set of paths that connect 2 points. As a closed form expression for the conformal factor is not given, we need to use a numerical optimizer to find the geodesic. In the optimization problem, the objective is the length of the path, which is given by the integral L of x is equal to z. Then finding the shortest path within 2 points in an arbitrary manifold is a high-dimensional multi-model problem that is more challenging than optimizing a single point. The initial path between the 2 points is represented by a straight line, whereas the dashed line shows the optimal path. The estimation of the conformal factor from the sample can result in infeasible areas having high values and feasible areas having low values. We introduce a positive time-dependent scaling function h of t greater than 0 to scale equation 10. The resulting geometric flow can be expressed as tau gt into tau t is equal to minus 2 h of t into Ricci flow. The Ricci flow on conformally flat manifolds exhibits an important property. As you can see in the left side, in the right side figure, visualization of the Cantwell environment, where the black regions represent unfeasible areas and the white regions represent feasible